Okay, welcome to chapter 17, section 3. Let's jump right into key ideas here. So, in talking about circuits, we want to talk about what's a closed circuit. What are the two ways that devices can be connected in a circuit? What happens to the energy that charges have in a circuit? Why is an overloaded circuit dangerous? So, what is a closed circuit? So the conducting path produced when a load such as a string of light bulbs is connected across a source of voltage, it's called a closed system. And that's when you have that it connects from one terminal on a battery all the way through to the other terminal, and there's no break in the path, or with a outlet anywhere where there's a voltage source and the conducting path, like wires and light bulbs and loads and things of that nature, are all connected from beginning all the way back to the end, or to the voltage source. So an electric circuit is basically a set of electrical components connected such that they provide one or more complete paths for the movement of charges. The voltage source, whether it be a battery or an outlet, is always part of the conducting path of a closed circuit. So without a complete path and a source of voltage, there is no charge flow and therefore no current. So no electricity flows at all. This is called an open circuit. So let's listen in here on this one.
A circuit is a complete path of an electric current. In order for electrons to flow through a circuit, the circuit must form a continuous loop. In this example, the circuit consists of a battery connected to a light bulb by two wires. When a continuous conductive loop is formed, current can pass through the circuit. When the electrons flow through the filament, the light bulb lights.
Okay, so switches interrupt the flow of charges in a circuit. You can use a switch to open and close a circuit. That's just like your light switch next to your door. When you flip it on, you're generally in the up direction, lights come on, you close the circuit there so electricity can flow. So when you turn it down or flip it off, you generally open the circuit and then all electricity stops. So no electricity is flowing. Schematic diagrams are something that are used to represent circuits, and they're a graphical representation, usually a drawing, of a circuit that uses lines to represent the wires and different symbols to represent the components in the circuit. All electrical devices can be described by some kind of schematic diagram, and they usually use standard symbols throughout the world so that everybody understands what each part of the circuit is. Here is some schematic diagrams and visual concepts here on the different parts. First part here, you have a wire or conductor that's just a straight line. In this case, it's got a right angle in it. That does not have to be a bent wire. It could be just a wire. It's just used to show you that that is a wire connecting certain parts of the circuit. Kind of a sawtooth type shape here. That is a resistor that resists the movement of charges. The next one is a light bulb. You can see it's kind of got like a globe around it with a resistor in it, and actually a filament in a light bulb is basically a high resistance filament or a piece of metal that glows very, very hot or very bright. Because of its resistance, it generates a lot of heat. That's what light bulbs are. Here, of course, a plug, a battery source, cells that you use to power the system. Of course, you got switch that can be opened or closed, and then lastly something called a capacitor, which stores electrical energy. So series and parallel circuits. So what are the two ways that devices can be connected in a circuit? That's series and parallel circuits. Electrical devices can be connected as a series circuit so that the voltage is divided among the devices. They can also be connected in parallel so that the voltage is the same across each device. Definition of a series circuit is a circuit in which the parts are all joined one after another such that the current in each part is the same. It's basically one conducting path all the way around, like one loop, where all the charges have to go through every part of the circuit, then back to the source. In a parallel circuit, that's a circuit in which the parts are joined in branches such that the potential difference across each part is the same. And this is kind of like having multiple loops all in one, to where there are multiple paths for electrons to follow in that particular circuit. So series circuits generally have a single path. When appliances or other devices connected in series, they form one single pathway for the charges to flow, and the current in each device is the same. The same amount of charge flows through each and every device. Although the resistances may be different, current is the same through each one of them. Because each one of them has current flowing through them that's the same, the voltage drop across each device in a series circuit can be different, though just because it has different resistances, the kind of push, so-called, the voltage, which is the push, may have to be stronger in some than in others because of higher resistances. So they'll get different voltages in the system. If one element along the path in a series circuit is removed, circuit will not work. It's basically like opening a switch. So let's see this visual concept here. On series circuits, you have resistors in series. Each of these are light bulbs. They're all connected. They go from one terminal of the battery through each individual light before they get back to the battery. And the schematic diagram here at the bottom represents that. You have your voltage source here to the right, and the electricity has to go through each and every light bulb before it then goes all the way back to the voltage source. So parallel circuits have multiple paths for current. Voltage across each device is the same as the voltage at the source now. So if you have a 6-volt battery, in this case the voltage across each individual light bulb is going to be 6 volt. It will be the same. Where in series circuit it would share the 6 volts. Like the 4 there would share 1.25 volts around each one of them, those 4 lights in the previous slide. So the current in each device does not have to be the same. The sum of the currents in all devices equals the total current, so it's kind of like a river that flows and goes into several branches, or goes around it. The water in each part of the branch is less than what the total current is, but as they all come back together, you still get the total current. So all of them branches would add up to what the total coming in and going out would be. Any break in one path in a parallel circuit, though, does not interrupt the electric flow in the other parts. The other parts still have a closed path. So as you can see here, these are hooked up in parallel. You have a battery, it comes out, the voltage can come through, or the electricity can come through, go at this junction where it's tied in here to the light bulb. It can go through the light bulb and then back to the battery here. It also can go to the second one, go across, and then back to the battery, go to the third one, across and back, and so forth. So you can see it can go from your voltage source in the schematic diagram out. It can go through the first filament or first light bulb and then right back to the battery, or it can go through the second one or the third one or the fourth one. And if any one of these, if we remove this 4th light bulb from it, all the other 3 light bulbs would still work. They would stay lit, where in the series circuit, if one is taken out, they all go out. So series and parallel here, when light bulbs are connected in series, charges pass through both parts, or in this case both light bulbs in a circuit, or all parts of the circuit. And in the parallel case, the charges only pass through one before they go back to the voltage source, and if one is removed, the other one stays on. Okay, so what happens to the energy that charges have in a circuit? Some of this energy is transformed into useful work, such as turning of a motor, and some's lost as heat. You can see sometimes like computers and TVs get hot. That's energy that's lost. So electrical power is the rate at which electrical energy is converted into other forms of energy. So electric power is calculated by multiplying the current times the voltage in a circuit. So power is equal to current times voltage, or P is equal to I times V, because the symbol for current is I, symbol for voltage is V. The SI units for power is the watt, which is equal to 1 volt ampere, or ampere volt there, or volt times an ampere. So if you combine the electrical power equation with the resistance equation, V equals IR, you can calculate power lost or dissipated by a resistor. You can calculate it several different ways depending on what information you're given. So if you take and replace, let's see, the voltage, take V and put it in for when you have I times V for power, you have I times R, which would give you I times R, which is I squared R. Or you replace it in other ways, you get something called V squared over R. So any one of those ways are ways that you can calculate power if you're given different parts of, or different information in the circuit. And electric companies measure energy in something called kilowatt hours, and 1 kilowatt hour is just the energy delivered to you in 1 hour at the rate of 1 kilowatt. So let's look at this short video here on electric power.
Electric power equals the product of current and the potential difference.
Okay, so short and sweet, electric power is P is equal to I times potential difference, which is V, voltage. So let's do some math skills here. When a hairdryer is plugged into a 120 volt outlet, the hairdryer has 9.1 amps of current in it. So what's the hairdryer's power rating? So again, list the givens and unknowns. We know that they gave us 120 volts is the voltage. The current that it has or was drawing was 9.1 amps. And what is unknown, what they want us to find, is what's the hairdryer's power rating. So we need to find the power. To do that, we'll write the equation first. Power is current times voltage. P is equal to I times V. We then insert the known values. The amperage or current is 9.1 amps and the voltage is 120 volts. So you multiply those two together and you get scientific notation 1.1 times 10 to the third power watts, or basically 1100 watts. So fuses and circuit breakers. So why is an overloaded circuit dangerous? High currents in overloaded circuits can cause fires. When electrical wires carry more than a safe level of current, the circuit is said to be overloaded. So if a wire's insulation wears down, two wires may touch and create an alternate pathway for current, or something called a short circuit. Fuses belt generally to prevent circuit overloads so that you don't have a short circuit. When you have a short circuit, it's basically electricity that arcs, creates a big spark and a pow, and it could ignite materials around it. So a fuse basically is just an electrical device that contains just a little metal strip that melts when the current in the circuit becomes too great. It's kind of like a resistor in that it has a certain resistance and it heats up so much that it will literally melt in two and close the circuit where you don't have a short circuit. Circuit breakers open circuits with high current. A circuit breaker is generally, in this case, a switch that opens a circuit automatically when the current exceeds a certain value. Circuit breaker just basically acts like a switch, and unlike fuses, circuit breakers can be reset by turning the switch back on. And fuses, if they melt in two, you have to go buy another fuse and replace it. Or circuit breakers, usually you just have to switch it, turn it off, and turn it right back on, and it should be fine. And if that doesn't do it, you got a short circuit somewhere else in the circuit that you need to have checked out. So let's see what this has to say about a fuse.
A fuse is a thin piece of metal encased in a glass tube. The fuse is placed in series with other components in a circuit. If too much current flows through the circuit, the metal filament in the fuse gets very hot and melts. The metal falls to the bottom of the glass tube. Since there is no longer a conductive path for the electrical current to flow through, the circuit stops working. Fuses are very cheap to replace and are designed to break quickly.